And then once I get to C, I can go back and forth to B. If I'm in A, I can stay at A too, but I can never get back to A. Okay, so this graph is not cyclic because, well, maybe you would call this cyclic because if you started in B, you'd get trapped in a cycle. Okay, so let's not worry whether it's cyclic, but these states are called transient, and these states are called absorbing. Okay, so in the limit, as I keep running this graph, I will eventually wind up in B or C, no matter where I start. If I start in A, I will eventually not be in A, although I may always have some probability of being there. It will never be 0. If I start in A with probability 1, I'll always have a non-zero probability of being in A. I can keep looping, but it's going down exponentially fast, right? So these are absorbing and transient states, right? And so you can think of, I've got like, see, I've got a more complicated example on the notes here. Okay, so here's cyclic ones. So this one is so this is a more complicated example. You can see that if you start in A and B, if you go to from A, you always either stay in A or go to B. In B, you either go to A. Often, 49 out of 100 times you'll stay in B, but 1 out of 100 times you'll leak out and get into C, D, E, or F. Once you're in this part, you just stay here and move around. And there's a very small chance of leaking out of this first part of the graph. But you will eventually leak out everything. Even if there's a very small probability of transitioning, you'll eventually leak out everything. So this does not count as ergodic. So it says for all values, it's going to be positive, and that's kind of in the limiting sense. At an infinite number of things, you will eventually be in 0.
So ergodicity can also depend upon the distribution with which we are starting, right? Or is it for all the possible distributions?
Well, so if it's ergodic, as I'll mention just in a minute or so, it's not going to matter where you start. There's going to be some cool properties that where you start is not going to matter. It's going to have certain properties. If it's not ergodic, what's going to happen will depend on where you start. The starting position will then matter. If you're cyclic, if you're in an even-odd cycle, it matters. The initial state, was it always in in A? That means if it was in A with probability 1 at state Q0, that means the even ones will be in A. If it was always in B, then the odd ones, then the even ones will always be in B, if Q0 was starting in B. If it had some probability of being in both, then it's going to be okay. It's going to stay having some probability of being in both. But it still counts as a cyclic graph because of that. If your state started in B or C, then it never will get to A. So you'll never have any probability of being this needs to hold, I guess, you may say this holds for all possible Q0 that this property holds. So and then if it's not connected, this is if, like, you have example where you have A and B, where you can go back and forth. You also have C and D over here, and these can go back and forth, but you can't get from one to the other, right? So this is not connected. So this is the other bad case. Right, so if you're not one of these three conditions, then, and this is kind of a theorem from mathematics that I'm not going to prove that holds, but if you're not one of these three conditions, then the Markov chain is on what's called ergodic. Okay, so why did I define this ergodic property? Well, if the Markov chain is going to be ergodic, and if you start with some model of a graph that doesn't satisfy this, there are ways of converting it into one that does, and we'll talk about these. But if it is ergodic, then some really cool properties happen. I'm going to go over this other part of the board here. So what we can do now is we can define some state distribution Q star, which is going to be equal to the the limit as n goes to infinity of Pn times of P to the n times Q0. Okay, so this is the limiting state for Q0 here. So if I start with Q0 and I multiply by this matrix, and I keep doing this, it's going to have a limit. It's going to converge to some distribution. Okay, you can only say this if this is ergodic. For instance, if it's cyclic, it's not going to converge. It may be alternating between two different states. If it's not connected, well, or if it's connected, the problem is that Q0 is the same for any initial state Q0. It does not depend on the state Q0. Okay, so this, if you think about, I was modeling a graph. I defined this Markov chain with this Q0 state. Well, this Q0 state had nothing to do with the graph, right? This was something outside, some other thing I added in. So if I don't want to worry about this Q0, well, if it's ergodic, I don't have to. It doesn't, this Q star state does not depend on my choice of Q0. So this is great. Okay. So that means, for all starting Q0, then so we'll call this limiting n to infinity of Pn. We'll call this P star. Then P star, then for Q, so for any Q, I multiply it by P star, I end up in Q star. And so this is pretty cool, right? So I could say I started half the time in E, half the time in D. I multiply it by this matrix P star, and I always get up to the value Q star. If I had a different state Q, and I multiply the matrix, I'm still going to get Q star. This is pretty weird. This P star matrix must be kind of special. So this is something cool's going on. So this is kind of what I'm getting at with this life lesson number 2 now, right? So just take it one step at a time. It doesn't matter where you started. You'll get there eventually, right? And I say you'll get there eventually, or you won't, because if you're in one of these absorbing or transients, have this absorbing transient property, or you're not connected, then this might not happen. But if you are, if the Markov chain is ergodic, you will eventually get everywhere, and you will eventually reach this distribution state in the end. this second cool thing, so this was kind of talking about this second view of Markov chains. But think about this first view where I'm always at a single state, okay? Then, so then I can say a random walk will be in state I with probability Q star I. So in the limit, if you're doing a random walk around the graph according to this probability transition matrix P, in the limit you will be in state I with this probability. If you walk long enough. So I walk for a long enough time, I'm like I go to the grocery store late at night. I just want to get out of the house. I start walking around the aisles. And I follow a particular pattern that I walk around the aisles. Then after I'm there long enough, you know, when the sun comes up in the morning, I can know the probability I will be in each spot in the grocery store. It'll be described by this Q star state. So that's pretty cool. So we'll use this when we talk about this metropolis I. This will be really the key property. And so this is, okay, so there's this other cool property. So this is one property. So the next property is that, this is a little bit hard to write down. So, yeah, okay, so Q star equals P star times Q star. Okay? So what does this mean? So if I start in this state Q star with this probability distribution of where I am, and I apply matrix P star, this also holds Q star is equal to P times Q star. Okay? So if I make one step, I'm still have the same distribution of where I am. Okay, so this only really works in this second view of it. Okay? And I'll explain a little bit when I talk about the metropolis algorithm, what's going on here. This view holds in the first view. But in the second view, it's saying I have some distribution of where I am. I kind of move forward. I have the same distribution where I am. Okay, so if I look at this example I worked through before here, okay, and what happened was in state Q1, half the time I was in A, half the time I was in B, and in Q2, a sixth of the time I was in A. So this changed, right? I was half the time to a sixth of the time. What's going to happen if I reach the final state, if I make a step forward, there can be, then what happened is everything stays the same probability. Seems pretty weird that this could happen, but that's what happened in this final state. So when I move forward, I'm not changing the probability of where I am. So there's also something special about this final state as well. Okay, so this is also useful that, you know, as I'm walking along and I keep getting to state, you know, Q0, Q1, Q2, Q3, and eventually state Qi, I'm getting closer and closer to this Q star. Now, it's not monotonically closer. It's hard, there's kind of weird properties where it can get closer and further away in certain cases. But kind of I'm, in general, getting closer. So if my starting state Q0 was very similar to Q star, I'm probably going to need less steps in the limit in order to really get there. Right? So if I'm starting close to Q star, I'm probably going to get there or get very close after a few steps. It's pretty tricky to try and formalize this notion. And if I start someplace like at all my probability is in B, or even worse probably, all my probability is in H, right? So with probability 1, I'm in H, probability 0, I'm someplace else. That's probably further away from the limiting state. So it's going to take longer, more steps before I'm really close to Q star. Right? So the closer you are to the right distribution, you know, the fewer steps until you're getting really close there. So I hope I have this in my notes on this, but I don't have Q star written down for this. So one thing that might be a little strange, this would be probably good to do, is that, so Q star is not going to be equal probability of being each of these states. Right? You could think, okay, I'm probably 1/8 of being in each of these states. That's not going to be Q star. Okay, so there's various ways of how to solve for this, but okay, yep.
Isn't Q star the eigenvector of P?
Yeah. So Q star turns out, so Q star is equal to the second eigenvector of P, right? So if you know linear algebra and eigenvectors and stuff, it's something where if you have an eigenvector is something that of a matrix is if you multiply it by this matrix, you get this vector back, right? Or maybe with some constant, right? And if you take the eigen decomposition of P, it's going to be the second eigenvector. So the first eigenvector is kind of just tells you whether the graph is connected or not. And the second one tells you is Q star or not. And actually the second eigenvalue
Should be 1.
so what?
Should be 1 if.
Well, so normally what you do is you make the first eigenvalue 1, you normalize the first one to be 1. And then the second eigenvalue is going to be smaller than 1. And how much smaller than 1 kind of tells you how long it takes to converge. So if it's very close to 1, it's probably going to converge really quickly. If it's further from 1, it'll take longer to converge.
So ergodicity seems like a desirable property.
Yeah.
How frequently do you encounter graphs that don't have that property? Like, is it like a tiny fraction you don't have to worry about it that often, or is it?
So probably, it depends on the sort of scenarios you're in, right? It's hard to find probability over graphs. So if you're talking about like social networks and web graphs, if you define things so that the edges are all undirected, as long as it's not size 2, then it's going to be organic, as long as it's also connected. Most of these social graphs are connected. Most of the web graph is not connected. You think of the web graph, and we'll talk about this on Monday, you think of web pages and the edges are hyperlinks from one web page to another. That graph is not connected, it's directed as well. And you want to use this directed property. Well, there's a trick you can use to make it organic. And basically you allow some chance of getting to, you kind of don't use exactly the graph, you modify it a little bit. And this changes the properties of it, but it actually changes it in a way that's desirable. And we'll spend some time explaining why this is. So if you're talking about discrete graphs like this, it's usually going to be not ergodic, but you can convert it into something that is ergodic. And I'm about to talk about this this metropolis algorithm. You kind of design, you kind of, there you're not really starting with a graph typically, you're starting with some probability distribution, and you design an algorithm so that there's an ergodic Markov chain. So it's kind of part of the design process, the modeling process, you need to worry about it being ergodic so that you get all these cool properties.
So the end game really is, it's not necessarily about the steps, but what the Q star ends up being to say, that's my probability of getting to someplace from someplace.
Yeah, well, so P star tells you the probability of getting from someplace eventually to someplace else. Q star tells you kind of this limiting state. And we'll see that this will kind of be like this, what's called the, not exactly this, but this will be like the PageRank vector. And it'll tell you kind of the importance of certain things. And we'll kind of build this up on Monday. Okay. So any questions on this?
So this is probably be good for like evaluating a system or something where you have like a bunch of, you're trying to, I don't know, design some sort of system for something and organize things you want to see work and then eventually converge to, rather than evaluating a decision.
Yeah, so this is on a graph here. So there are these continuous versions of this, right? Where the state does not need to be discrete. It could be the amount of money you have is actually discrete. But imagine you have enough money that the cents kind of blend together or something, or it's in this, I don't know. So you could leave different values describing your states as being continuous set of values, and then it could model the system. Yeah, so there's lots of ideas of modeling systems like this. This is a very powerful tool. Yeah.
So for the graph that we have here, can we say that the Q star would be the number of links to each node divided by the number of all other links? Which means that
No, it's not exactly that. I feel that it's kind of silly that I didn't work out what Q star was for this graph. I'll try and do it and post it on the discussion forum or something. But it's not so simple. So you need to, I mean, the eigenvectors of these graphs could be kind of strange. So we solved for the eigenvector of this graph in an earlier lecture. Let's see if I can find this quicker. Right, so I think it was the same graph, because I just reuse it over again. Okay, so the eigenvector here I think I did this. So no, I did the eigenvector of the Laplacian. Okay, so I did the eigenvector of the Laplacian, so I don't even have this in my notes. But if someone wants to kind of code up this matrix and run the eigenvalue decomposition, we can get out the eigenvector out of this. So it's going to be it's going to be different than the dividing through there. So if you did this, so you want to say so this value h is going to be much smaller. The q star value, but probably being h is going to be smaller than being in these other states. What happens is if you're in here, you tend to stay in this part of the graph. If you're in h, once you leave, then it's hard to get back here. You have to be in f to get back there, and then if you're in f, only 1/3 of the time out of here do you end up in h. If you're in f, 2/3 of the time you don't go to h. if you're in H, you always leave H, right? So this is gonna be small, right? All right, so I apologize for not having Q star. Let me explain the metropolis algorithm, and this will give you a different view of how you can use this. And this is another really cool algorithm. So this is called the metropolis. The metropolis algorithm. Sometimes the metropolis hastening algorithm for different versions of it. So this was from a paper by Metropolis, Rosenbluth, Teller in 1953. There's another paper by Hastings in 1970 which kind of showed some more general applications of it. And so it's by these five authors. Rosenbluth, this was a husband and wife pair. Teller and Teller were a husband and wife pair. Metropolis was kind of off on his, was I don't know if he was married or not. But his name was first alphabetically, and I guess it's a little bit cooler than these other names. So he somehow gets all the credit for this. It's actually fairly controversial whether he should have gotten the credit or whether one of the tellers really was kind of the main person behind it. I've read different accounts of history. But this was important. This was 1953. So this is when it was published, but the work was actually, that led to this, was going on in the early 1940s. And this came out of the Manhattan Project. So there's this really cool ideas back there about these sampling from this, how to understand complex systems as you were describing. And they could define local transitions of these complex systems, but they didn't know how things wound up. And they're trying to model things related to the atomic bomb, actually. They're trying to understand these simulations of the atomic bomb, and we were just starting to get computers. And so you could somehow, if you could compute some of these things using some experiments, some simulations, you wouldn't have to work out these complex things by hand. Okay? And so for the graph, you could write this down, you can do the eigenvector decomposition. You could do it by hand, although it'd be really probably pretty painful, but people were used to doing fairly painful calculations back then. A computer used to be referring to a person who sat down and did actually calculations. So you could have done this if you had a graph, but we're in a slightly different setting here, where so you have a set of these states. So in each state, V in W is associated with a weight, W of V, and we'll say that big W is going to be the sum over all of these states of W. Or in general, the set of states may be actually continuous, and so then it would be an integration over V over this thing of these weights. So it's some integral. It could be an integral over a continuous number of states. And this is, so you're going to have this setting where for any particular state, you can calculate some sort of weights associated with it. But you don't know this capital W, the sum of all the weights, or the integral of all the weights. Okay? It could be that the number of states is just huge. So think of, it could be a thing where there's kind of some exponential number in terms of the problem size. Like, think of if you describe you say all IP addresses have some probability of being at them. Well, you describe the IP address just by the value of it, but the number of IP addresses is enormous. right, is too big to calculate to even take a sum. Right? So it could be an exponential number or it could be continuous. And we in general have no way of calculating W. But what you want to do, the goal is to sample some set x1, x2, up to, say, xn, each of these proportional to the weight of the state over this capital W. Right? So you want to sample a set of these values from the state space proportional to their weights. Okay, so if the weight is higher, I'm going to more likely sample from this. Okay. And hopefully I've somewhat convinced you in this class that if you sample from some distribution of things, you get a pretty good, you get a lot of properties about this underlying data set. You can get a lot of good properties from it. And this was very useful in, say, a set of these states have some, have some sort of condition, like you're developing this atomic bomb, and this is certain of these states correspond with things that would actually be, that would be something bad. You want to know the probability of it being bad. So you want to know the probability of being in part of the state space. So you want to sample a bunch of these, and then look at what fraction of them are in this bad part of the state space. In order to do that, you need to sample them proportional to this weight. Okay, and you have this, and all you have is this weight of these things associated. Okay. So one important application of the more modern application is in understanding protein folding. Okay, so now a state space is like a configuration of a protein where you have where all the atoms are, and you have an energy associated with them, and that's this weight. Actually, the energy for the protein folding is typically something like e to the minus some constant times the energy of V. So you can calculate this energy function, you do e to the minus this, and this gives you a weight. So the larger the energy, the less likely you are going to be in there. This is called, it's like the Boltzmann function. And so people use these models, they just know this energy, and they say you're less likely to be in a higher energy state, more likely to be in a low energy state. Okay, so I want to sample something proportional to the energy. And this directly maps to the sort of states you tend to see proteins in. And understanding how you can transition between states, this is critical, understanding the alpha model with something that looks like a Markov chain. Okay. Okay, so we somehow want to do this, and all we're given is this weight function that we can evaluate. That's the only thing we can do. So what we're going to do is we're going to create a Markov chain, and we're going to use this view 1 to kind of do a random walk in the state space, and after we randomly walk long enough, we're going to be in some state Q star. We want Q star to be exactly this. Okay? So, so I just need to find this this random walk. So this energy is for protein folding is not unique to there. It's also an energy of these systems they were studying for the nuclear bomb and so forth. So for this random walk, I'm going to start. So I'm going to, I'm going to have this loop where I'm going to start at a state Qi. Okay, and so what I'm going to do is, so I'm going to start by generating a state, a potential state U, or let's call this state P, which is going to be proportional to some neighborhood around QI. So in many cases, you may use like a kernel, and this may be like a Gaussian kernel. It could be, I'm going to pick some random point within some distance. Or I'm going to pick, if I have a graph, I'm going to pick a random neighbor on the graph. Okay? Okay, and then, but I haven't incorporated this weight yet. And actually, the choice of this is not going to matter in the properties. It's going to matter in the efficiency of the algorithm. So then, with probability, let's see. So if the weight of P is greater or equal to the weight of Qi, then I'm going to say Qi plus 1 is equal to P. So if I happen to move somewhere in my neighborhood to some larger weight state, I'm going to say, okay, that's the next step I'm going to do in my random walk. Else, I'm going to say with probability weight of P over weight of Qi, set Qi equals to P, pi plus 1. So if this weight is like half as big as the previous weight, then half the time I'm going to choose P as the next state. So sometimes I still keep it even if the weight is smaller. But if it's much smaller, I'm less likely to keep it. So if I'm thinking of energy, if I move to a higher energy state, and the Boltzmann conversion is much lower, I'm much less likely going to kind of move there in some kind of, random walk in this energy space. So otherwise, I'm going to set Qi plus 1 equals to Qi. It means I'll stay in the same spot. So my random walk will stay still. And this property where I have a chance of staying in the same spot, that makes sure that this process is not going to be cyclic. I can't get into any loops. So because I always have, as long as this weight is always, so this is the random walk, and this actually implicitly describes this probability transition matrix.